Greetings, welcome to the topic of energy, okay, which exists all around us, okay. But when it comes to energy, there are two types, okay, that we must know. You may or may not have heard of these two: kinetic energy and potential energy. Okay, and there are formulae for both. In other words, they both can be calculated. Okay, now let's have a look at the first one, which is kinetic energy. Okay, let's define it. Okay, let's give it a little bit of a definition. Okay, which is normal English definition. Okay, kinetic energy is defined as the quantity of energy. Okay, it's the quantity of energy an object possesses. Okay, let's write it underneath here because we don't want to run out of space. Because of its motion or due to its motion. So it's energy of a moving object, essentially. Okay, that's what kinetic energy is. The energy an object has due to movement. Okay, so again, it's safe to say that all moving objects have kinetic energy, and we calculate using the kinetic energy using the following formula. We use the symbol EK, E for energy, K for kinetic energy. So I know it's kind of written back to front, but EK is equal to half mv squared, where m is equal to the mass of the object in kilograms. V is equal to the object's velocity, okay, which we know from the equations of motion, etc., is meters per second. Okay, so half the object's mass times its velocity squared will give you the object's kinetic energy. All right. Okay, now this is a bit more simpler to understand and simpler to grasp than its other cousin, which is potential energy, and sometimes referred to as its full name as gravitational potential energy, okay, which you're going to have a look at on the next slide. Gravitational potential energy is its cousin or its full name, all right, often just referred to as potential energy. Energy an object possesses because of its position in the gravitational field relative to a reference point is what is known as potential energy or gravitational potential energy. And potential energy, of course, is associated with a force. Okay, now in grade 9 natural science, when we first introduced force, we know that a force is either a push or a pull, and we measure it in newtons, all right, denoted by capital N. All right, I'll put in brackets here, capital N for newtons. Okay. Any mass near other masses actually has gravitational potential energy. Okay, so the force that gravitational potential energy is associated with is obviously the force of gravity. Okay, talking about the force of gravity, which we're going to use as Fg, is also equal to weight, which is also equal to mass times gravity. Okay, so now when we have potential energy, we actually use this little bit in the potential energy formula. Okay, so the potential energy formula, which I'm going to use a different color for, okay, is EP, potential, P for potential, E for energy, is equal to mass times gravity times height. Okay, where mg being the weight of the object and the height being the position or the reference point of that object above ground, etc., etc. Okay, so if we take a look at an example, a rock of a mass that has a mass of m, all right, unknown mass, in the gravitational field of Earth has a gravitational potential energy because of the force of gravity, which is just the first part of that formula, mass times gravity. The rock and the Earth will obviously interact with each other, and we'll say that the rock has potential energy due to its position. So if a rock is on a cliff and the cliff is at least 200 meters above the ground or above sea level, then of course because I'm picturing a cliff and there's ocean at the bottom. So then, of course, that position that it is 200 meters above the earth or above the above the sea level, then obviously means now that we can calculate its potential energy, because it does have a mass. It is encountering gravity, and of course, where's it positioned? It's actually 200 meters above the ground, or at a height of 200, until you chuck it off, and then it obviously, that energy, the potential energy that it had, converts to kinetic energy, because it's falling to its rocky death. If it were alive, of course, but it's not. It's dead. It's an inanimate object. Okay, so a more accurate definition for H in the formula there is measured in respect to the reference level, all right, taken as 0 level. So to just specify, of course, mass is in kilograms, gravity 9.8 times, or just 9.8 meters per second squared. You know, H is equal to the height in the formula, and that's measured in meters. Okay. Now, what do we measure energy in? Okay. Energy is measured in joules. Okay, and I write it as capital because your answer, for example, if it were 280, that was the either potential or potential or kinetic energy. And it was 280 was the value. Obviously, you'd measure it as 280 joules. Okay, capital J. All right. Cool. So now what we're going to do is we're going to introduce the third type of energy, known as mechanical energy. Now, mechanical energy is basically EM. The formula is equal to the sum of potential energy plus kinetic energy of a particular object. Alright, it's the sum of the gravitational and the kinetic energy of an object or system of objects at any moment or at any point in time. No real definition for it though, okay, just to understand what it is. Okay, but this over here is the formula for it. It does not leave, it stays all the way, and it gets modified a bit though in metric. Okay, but there is a law that does come with this type of energy. There's a law. Okay, we're going to aim to explain it quickly, and it's called the law of conservation of energy, or mechanical energy. Okay, and this is what it states. In a different color, I will write it. While energy can be transferred, from one object to another, the total quantity of energy in a system remains constant or remains the same. Okay, and energy cannot be created or destroyed, it can only be transferred. Okay, it's created once, it exists once, can be transferred. Okay, cool. So in other words, we have the formula, of course, EM is equal to EP plus EK, obviously keeping everything constant or in an isolated system, okay? Because that means if only the force acting on an object is its weight, weight meaning mass times gravity, if that's the only force that is acting on an object, it's its weight, then the total mechanical energy will just be the sum of its potential plus the EK, alright, or the object's kinetic energy, making that system up to be constant. Okay. However, there are some examples where there is a shift. Okay. And that example exists for a roller coaster. A roller coaster obviously means that you are at different points. Alright, your kinetic energy changes as you go on a roller coaster. In other words, you go because your velocity changes. The roller coaster has parts in the roller coaster or sections where you go faster, some where you go a bit slower. Okay, I'm sure we all remember Retunga Junction. Any of us been on the Cobra just before they closed down? Not sure if you were on the Cobra, but the Cobra was obviously my favorite ride. I remember once going on there and going 6 times in a row. I was there early, so no one was there, so all of us, we just went after each other 6 times in a row. Anyway, so a roller coaster is an example where the object moves between 2 different or more than one location. So let's say we have 2 locations, we have A and B. So let's draw a basic. Okay, let's do that. So maybe that's a 2D roller coaster pattern. So we know a roller coaster obviously goes up, gets to this point here, which is point A, goes down that way and ends up here at point B. Okay, and obviously these are all at different heights. This is H1, height 1, and this is height number 2. Okay, so now if mechanical energy is conserved for an object that moves between 2 locations or more than one location, for example, just A and B, then total mechanical energy of the object at A must also equal what it is at B. That is only if it is conserved, and we assume that it is. So then we end up with a new formula, okay, for at these 2 different locations. We end up with a new formula saying that actually use a different color, orange, that mechanical energy at point A must equal mechanical energy at point B, meaning potential energy plus kinetic energy all at point A must equal the same thing. So potential energy at point B plus kinetic energy at point B. Now we know that each formula for both, okay, mgh plus half mv squared. This is a great way to determine what was the velocity. If we're given the velocity at point A, what is the velocity at point B? So to further write out this formula, mgh at A plus half mv squared, sorry, write the square on top there, at A is also equal to mgh at point B plus half mv squared at point B as well. And this is how we can find any of the missing variables if given a scenario. Alright. So just for the purpose of the recording, we are taking the grade 10 DBE November paper, and we're looking at the energy question in the paper, which is question 5. And it's for 13 marks. Very nice question. A steel ball of mass 5 kgs is rolling over a frictionless surface, as shown below. When the ball reaches point A, it has mechanical energy of 250 joules. And the sketch is not drawn to scale. State the principle of the conservation of mechanical energy in words. And I'm sure this was quite basic to say, because I mean it was on the previous page. Okay, an easier way to say it for exam purposes, all right, is simply that the total, okay, and I would encourage you ladies to remember this one. Okay, so take this down. The total mechanical energy in an isolated system is constant or is conserved. So I'll say is conserved or slash constant or system remains the same. Okay, so however you end it off is fine, but the first part, total mechanical energy in an isolated system, that part stays the same. Either is conserved or is constant, or right after that remains the same. 5.2.1. Use your knowledge of principle of conservation of mechanical energy to write down the kinetic energy of the steel ball at point B. Okay, so at point A, which looks to be more or less in line with point C, looks like that's about 5 meters off the ground as well. Just looking at it, not drawn to scale, of course. B is on the ground, on the dotted line. The dotted line represents the ground level or the ground floor, or ground level, surface level. So if my mechanical energy formula is EM is equal to potential energy plus kinetic energy, then it's safe to say that because there's no height at point B, height is equal to 0, that there is now no longer potential energy as that's 0. So therefore mechanical energy equals to just the object's kinetic energy. Now in the question it said at point A, the mechanical energy is 250 joules. Okay? So, at A, okay, now they want to know what is the object's kinetic energy at point B. And we were given EM. Right? They said EM is equal to 250 joules. So let's substitute. 250 is equal to EK. Therefore, the object's kinetic energy at point B is equal to 250 joules. And there's your answer. It's 2 marks, so you only have to write down this part. But there's your answer. 5.2.2, I think, asked for the velocity or the speed of the steel ball at the instant it reaches point C, which is 5 meters above the ground. Now the conservation of mechanical energy does come into play. Now we say EM at point A should be equal, if it is conserved, to mechanical energy at point C. So in other words, we have EP, alright, plus or at A, plus EK at A should be equal to EP at point C plus EK at point C. Now we know what this part is equal to because it says the mechanical energy at A is 250 joules. So we simply sub in and say 250 is equal to, and now we start and we unpack these two variables, saying, well, EP is equal to mgh plus half mv squared. It really doesn't matter if you say EK plus EP, half mv squared plus mgh, it's still the same thing, it doesn't really matter. And now we just substitute in, okay? So, 250 is equal to the mass, which is 5, gravity is 9,8, and the height at point C is 5, plus half of 5 times v squared, which is unknown. Okay, we don't know what v squared is equal to. Okay, we just get my calculator quickly, which is next to me. So 5 times 9,8 times 5 gives me, well, 250 is equal to 245, plus half of 5 is 2.5. Okay, in fraction term, that'll be 5 over 2 actually. But anyway, just leave it at 2.5 v squared. Leave it in this decimal thing. That's okay. So then, let's see. Okay. So 250 minus 245 gives me 5. Is equal to 2.5 v squared. Divide both sides by 5. 5 divided by 2.5 gives me 2. So v squared is going to equal to 2. And then we're going to square root both sides. And up top here, therefore, velocity is going to equal, square root answer, 1,414, so, and a bunch of other numbers, so we round off to 2 decimal places, 1,41 meters per second. And that is our final answer for 5.2.2. So question asks what happened to the 245. So you can see this is a positive number and that's a positive number. When that goes over here, 215 minus 245 gives us 5. 5.3 says determine whether the mechanical energy is required, or determine whether the mechanical energy acquired by the ball at point A will be enough to carry the ball over point D. Okay? Let's have a look again at that question before we begin to do anything, because that question is or does sound like a question that might just bamboozle a lot of students. So you might have to read this one a little slower, even for someone like me who's been doing this for a while. Determine whether the mechanical energy acquired by the ball at point A, which we know is 250 joules, will be enough to carry the ball over point D. Okay? So we need to go and we need to prove that. Okay? Or to say whether it will or whether it will be able to. Okay. So what we can do to show because they ask us to show the calculation, so we don't have to write it or use some English words or use our words to be able to determine that as well. They just want us to show the calculation. So we'd use mechanical energy at point D, which that looks like P. Let me just D must be equal to, of course, EP at point D plus EK at point D. If we look at point D, we know that's 7 meters above. Okay, so we find out what is the mechanical energy. Firstly, we can see that it looks like it comes to a stop at point D. Okay, so looks like that's where it ends. Okay, so what do? Is we assume that kinetic energy is equal to 0, so we only end up with mgh. So the mass there is 5 times 9,8 times the height now, which is 7. And let's see what is the mechanical energy there, which is equal to the potential energy at point D. Okay, EM at point D is going to give us 5 times 9.8 times 7. That's going to give us 343 joules. And the mechanical energy at point A was only equal to 250 joules. So, based on this information, again the question is, determine where the mechanical energy acquired, alright, by the ball at point A will be enough to carry the ball over to point D. Okay, so basically, for about, let's see, how many marks is that? 4 marks. Okay, we are going to state that the minimum energy needed for the ball to reach point D is 340 joules. The mechanical energy of the steel ball is 250 joules at point A, which is less than at D. So the ball will not reach point D. Alright, cool. So let's write this out. So the minimum energy needed or required for the steel ball to reach point D, or just to reach D, is 343 joules. Okay, the mechanical energy of the steel ball acquired at A is 250 joules. Okay? Less than at point D. Therefore, the ball won't reach point D. Alright, and that's our final answer for 5.3 for 4 marks. We get a mark for the calculation. Alright, and then we get another 3 marks for stating all this. And with this question, we end off circuits. Wow. We end off the topic energy. Next week we'll have a look at some further exam questions and make that just a question-based lesson. Grade 10s, we will go through some exam papers of this topic and exam questions of this topic, of course, preparing us for when we actually get the topic in our exams of this year.